So we have Professor Giulia Galli today with us. So she's the Liew Family Professor of Electronic Extraction and Simulations in the School of Molecular Engineering at the University of Chicago, Department of Mechanical Engineering. She's also a senior scientist position at the Argonne National Laboratory. So probably all of you that are familiar with the field, you know her very well. So she's really outstanding scientist with like many awards and many prizes. She's also a member of the National Academy of Science and the American Academy of Arts and Science and the American Association for the Advancement of Science, International Academy of Quantum Molecular Science. I think that today she's gonna talk about the quantum embedding methods for simulations and materials on quantum computers. So her expertise is also in the development of theoretical and computational methods. So thanks a lot, Giulia, for joining us today, and it's all yours, so go ahead.
Okay, thanks so much for the invitation. And as you know, originally I had hoped to travel to Boston, and then we are still in this limbo, and here I am on Zoom again, but I'm glad to be here. I must admit that I'm not sure this will be my best talk. I'm just coming from a discussion with a grad student of mine who's from Ukraine, and we have been talking also with my group of what's happening. So we are all very shaken, as I'm sure all of you, but I'll try to focus on the talk. And again, I'm really happy to be here. And I'm going to tell you about a development that in my group is relatively new. It started a couple of years ago, and it was motivated by a specific problem that we are interested in solving, a problem on spin qubits, to look at spin prediction of property of spin qubits for quantum technologies. And it led us to think how to do calculation for materials on a quantum computer. But I would like to start with a sort of general introduction to put in perspective what we're doing. So the reason why I'm doing that is also because looking at the website of your of the CSC at MIT, I saw that probably there is a kind of a heterogeneous audience, not only materials people, but so we are studying materials at the microscopic scale. So for us, a material is a solid or liquid or a nanostructures, and it's a bunch of nuclear coordinates to say where the atoms are, and wave function to say where the electrons are. And in principle, we would like to just solve the Schrödinger equation. In practice, what we do in my group is to limit ourselves to the time-independent Schrödinger equation. So we spend basically our life to solve eigenvalue problems. So we have a Hamiltonian of the electrons and the wave function, and we want to understand the ground state properties of electrons in the field of nuclei, because we are interested about the structure of the material, thermodynamic and vibrational properties. And of course, we're also interested in the interaction of a material with light, right? We want to do spectroscopy to understand whether our models are right. And because a number of problems like photoelectrochemistry or optical addressing of spin defect for qubits, many properties have to do with the interaction of light and matter. So how do we solve this equation? The strategies that people have come up with, say, if we look at the last 60, 70 years or so, are density functional theory, which I think probably most of you, even if you're not in the field, have heard about. It was born within condensed matter physics. It was then also applied to molecules, and it's an exact theory which is only applied in an approximate ways, because there are the functionals that it's based upon are unknown, and we need to approximate them. Quantum chemistry was born before density functional theory, way before, with Hartree-Fock in the chemistry world. It has been used for really a myriad of molecules and also some solids, and it has been very key to the development of what we call today hybrid functionals, or these approximate functionals. So really, quantum chemistry is intimately now related to density functional theory, which would workhorse of material science. And then quantum Monte Carlo, I will not talk about this today at all, But I just want to mention it was also born with condensed matter physics, and it also intimately related to density functional theory, because it is because of quantum Monte Carlo calculation to solve the eigenvalue problem, the Schrödinger equation, that were done in the 80s by Seppelin and Alder, that we have approximation that made possible the use of density functional theory. Without those calculations, more than 40 years now, we would not have, the local density approximation and so on and so forth that we are using in density functional theory. So what are we doing when we solve the problem? We solve self-consistent. We do self-consistent solution of coupled, nonlinear, partial differential equations. Of course, as we all know, the Schrödinger equation is linear. But with all the approximation that we come up with, we end up solving coupled, nonlinear partial differential equation with constraints. I am showing at least one equation here. These, of course, are very famous equation, Kohn-Sham equations. And just to tell you what they are, they have a term that depends on the solution, this V. Not only that, this term has a component that is not known and that we approximate. This is the component that I told you we approximate when we do all of our calculations. These are equations with constraints. They are in green down in the slide, and the constraint is a constraint of the total number of electrons, and the constraint comes from the fact that electrons are fermions. Okay. So this gives us, by the way, these types of equations are the basic equation that are always also solved when you do quantum chemistry, because somehow you need some input that has something to do with Hartree-Fock before going to higher methods. So this is always kind of there. It's not there in quantum Monte Carlo, but as I said, I won't talk about that. Okay, so if you do this, you barely know how the electron behave in a solid or on a molecule at T equals 0, and you start understanding actually quite a lot about bonding. So if you want to include temperature effect, and you want to explore, for example, phase space of a material, well, you can start by coupling DFT with molecular dynamics. So you solve F equal ma. You need to know where your F, the force acting on the nuclei in your solid is, and you compute it from density functional theory. This E, capital E there, is a total energy that you actually get by solving those equations. Sometimes this is not accurate enough because, for example, your ions are light, like hydrogen, carbon, or whatnot, and you need to do better. Then you can couple, instead of coupling your density functional theory, your favorite method for electronic structure with MD, you couple it with what we call path integral. Use Feynman paths to define a collection of variables that are able in somehow, and Bruce Byrne was one of the first to do this at Columbia, were able to capture the quantum nature of the nuclei. Of course, there are problems where you don't only need to understand the dynamics or the thermodynamics property, but you want to do sampling of very complicated surfaces in phase space for your system, and you want to add bias to your system in some way with forces or in, coming up with methods like metadynamics to sample phase space. So basically, this is what we do. And by we, I mean, we are contributing to calculation using those methods, but we, I mean, as a community in condensed matter and also quantum chemistry. And let me give you just in pictures a idea of the examples. And these examples are taken from my work, because I'm here to talk about my work and in a way, to promote my group. But of course, many people in the world and in the community are doing many calculations that are very interesting, and some of them along the lines as the one that we are doing, for example, using all the machinery that I briefly sketch, we can do calculation like looking at electrochemistry problem, looking at solid liquid interfaces, that is a silicon surface interface with water, and do calculation even in the presence of electric fields. Or we can do calculation related to photoelectrochemistry. I didn't mention that on top of all this calculation, we could also do excited states of electrons. I'll get back to that. And this is a paper, a review paper that we wrote recently to summarize some of these calculations. And these are all, calculations where we couple some approximate forms of DFT with molecular dynamics. You can also couple with path integral molecular dynamics. We have done so recently to ask the question, if you have a light system, which is in so many problems like carbon, which can be disordered like amorphous carbon or crystalline or molecular. And what happens to its electronic property if you take into account the nuclear quantum motion? And we have found, very, very interesting effect. And this is an example about formation of spin defects where we have coupled the first principle molecular dynamics with advanced sampling techniques to understand when you have, for example, two isolated defects in silicon carbide, a missing silicon or a missing carbon, how they come together to form a defect that is interesting for quantum technologies. And we have an interest in defects for quantum technology that I will get back to in 5 minutes or so. And semiconductors are not the only system of interest for defects, but also transition metal oxide, as specifically in recent years, we have been attracted to problems like oxygen vacancies in oxides that have also some real interesting connection to creating resistive states for neuromorphic devices. So this in pictures gives you an idea of how broad the applicability of these methods is when you use classical computers. So now how do we solve the electronic structure problem if we want to use a quantum computer? Of course, the very first question is, why would you want to use a quantum computer, right? And what's the interest there? Well, I think our interest, like the interest of course, of many other people, is we want to learn how, to use, how to define a problem, and if we can address some of the problems that are present with quantum computers, and also understand the noise. So the all devices that are in quantum computers are noisy. The hardware is noisy. Can we do something even with these noisy devices? So really the question has been a question of let's try to learn, while these technologies are emerging, to understand whether we can be positioned one day to use these computers. As you will see, we are incredibly far from addressing any of these very complicated material science problem on a quantum computer, really, really very far. And so what I'm telling you from here on, this kind of ends my long introduction that I always tell my students not to do. Just don't do this incredibly long introduction. I just did that. So this ends my introduction, and I will tell you, we go back to addressing simpler problem, and we want to learn how to use quantum computer. Okay, so let's try to, so how do you do that? The answer is focus on where the action is in the solid, if you can. So let me try to understand, to explain to you what I mean. So there are problems, like for example, a spin defects here in a solid. So you have a solid, say diamond, and you generate a defect. Like you remove an atom and you put a nitrogen atom, or a silicon carbide, you put two vacancies. And the electronic properties of this defect there are interesting, like here, like shown here. They are interesting to realize a two-level system that can be a spin qubit, that you may use for quantum technologies, sensing, even quantum computing or quantum communication. So the action is where the defect is. And so, of course, if you want to focus on that, you need to be able to focus on that, but also to come up with a way of taking into account all the solids around the defects, right? And what I mean by if you can, what I mean is that you may be able to do this if electronically the action is really localized. And this, in terms of electronic structure, I can do that if my electronic states that do the action that I'm interested in are localized in a certain region. You know, there are other defects that are much more shallow, for which this would be what I will be talking about, much more difficult. So I will show you results for this system that are realistic system, taking into account all the environment on quantum hardware. And the quantum hardware is IBM Casablanca that we had access to, we have access to through Argonne National Lab. Okay. So here there is another equation, but you know, not very many. So basically, we want to isolate this defect within the solid. We want to define an active space and understand the action of the rest of the system, this WR here, on the active space. This is no news to quantum chemists, right? They have been coming up with ideas on how to deal with active space for many, many years before us in condensed matter and material science. And so what's actually kind of difficult here, and that we thought about, is how within a solid we build a quantum embedding that take into account all the environment around, okay? And if we do this, we can build an effective Hamiltonian in second quantization, this is a operator here, with terms, this T single particle and multi-particle V, with terms that take into account the solid. Okay, so we pick a problem that physically makes sense, where we can actually relegate the action to a certain region. We build an active space. We don't divide by region, we divide by active space. And we have a means to take into account all the action of the solid on the active space to build an effective Hamiltonian. Okay, so not the first one either to think about quantum embedding. So our contribution to that has been to find a way to compute this effective interaction here, which I call screened Coulomb potential. It's a potential that takes into account the correlation between electrons in the solid in such a way that we could really study a large realistic system. So here there is a little bit of jargon, and maybe the expert will understand that, but let me try to explain this in general. The reason why we were able to actually compute this term here, the action of the environment on the active space, to build this effective Hamiltonian by taking into account many atoms, like 500 around the defects, hence the strain fields that are necessary. The reason why we were able to do that is because in the last 10 years, actually even more than 10, we spent a lot of time to compute exactly terms that are similar to those when trying to solve Dyson equations. These are equations, approximate forms that we learn how to solve to study electronic excited states, to do GW and Bethe-Salpeter equation calculation. Because we came up with these algorithms, spectral decomposition of dielectric matrices and so on and so forth, we actually were able to compute this for these realistic system quite fast. And now we have an embedding theory, which is scalable to large system containing hundreds of atoms, meaning we can look at realistic systems. Okay, so this is the embedding theory that we will be using to go and solve this Hamiltonian on a quantum computer as well. Quantum embedding is, of course, not our invention. There are many people that have been working on quantum embedding in many different flavors. The point of this slide is not to explain the flavors or not even the acronym, but just to tell you that we built this quantum embedding and this way of computing the effect of the environment on the active space based on Green's function formalism that also other like dynamical meaning field theory used. But there are many interesting quantum embedding theory based on density matrices and also on the density. And we wrote a short review that actually some referee didn't like at all. This is why, you know, we submitted it a long time ago, but it's still there. Anyway, we wrote a short review to compare these methods and hopefully, you know, we'll get it right. And at some point it will be published and maybe it will be useful. Anyway, so what is the strategy? The strategy is to write an effective Hamiltonian. I just told you we use quantum embedding to build it. And of course, we need to use all the machinery that we used over the years, knowing how to solve Dept, how to solve excited states to get these terms here, T and V, on a classical computer. These terms are not gotten, we don't get them on a quantum computer. We pre-compute them. We solve the effective Hamiltonian on a quantum computer. And how do we do this? We represent the Hamiltonians in terms of qubits and quantum gates, and there are transformed to do that have been, you know, the first one is 1927, I think, or something. Of course, not for a quantum computer, but to transform the Hamiltonian into Pauli correlator. And we did not implement this, but we used the implementation of these transform into open source codes that have been put out there by IBM. We use Qiskit because also we use IBM machines, but also OpenFermium by Google and by others. Once you have done this, you need to choose an algorithm. And here we are again to solve an eigenvalue problem like we have done for you know, zillions of years. And you have to choose it compatible with the circuit hardware. I mean, this to some extent we also do on a classical computer, right? Because if you want to parallelize and all, but in this case, it's much more complicated. And we need to deal with noise. So now I want to tell you about what we do about that. But let me tell you that, you know, people in the quantum chemistry world and in the molecular world started looking at these problems on how to do this on a quantum computer already some time ago. And this is a nice review paper. And this is not our paper, it's you can download it here. And I don't want you to look at everything, but just to look at the column in the middle, which says systems, that gives you an idea of the systems that people have been doing on a quantum computer for molecules. And, you know, we are very far from the type of complexity. I told you about the complexity in the material science world when I showed you all this picture, but there is an equivalent complexity or even more in the quantum chemistry world where people can solve incredible problem of quantum computer today using quantum chemistry method. And here we are going back to very small problem, right? The H3, this is a, you know, a calculation of again, these are taken from the literature, calculation of the potential energy surface of I think this is H3 and this is lithium hydride. The reason why I show the picture in the middle and is because it's one of the picture that showed you the results that comes, all these points, not the blue one that comes out from the machine, and the blue one that are noise mitigated. And this is also what I will show you in our example. Okay, so lots of progress already in the quantum chemistry world in attacking these problems. And now we are trying to use and build on what people have done and do problem in the solid state. Okay, so we have our Hamiltonian. We have to transform it on a qubit Hamiltonian. That is, if you know the term, we need to have transform it in a linear combination of operator, then our Pauli correlator. But the point is, we need to have an ansatz for the many-body wave function. And as I'll show you, we have to have a way to enforce particle conservation. So let's pause for a moment just before solving this equation to think that, I started telling you about density functional theory, quantum chemistry, and the spirit about, that has been used for many years to do calculation about self-consistent, non-coupled, the differential equation. Here, totally different strategy. We write an effective Hamiltonian in second quantization, and we want to diagonalize it. No self-consistency, no nothing. We just want to diagonalize it. And we want to compare it with full CI, full diagonalization on a quantum computer. Of course, everything we have learned for many years is here, right? Let me remind you, it's in these T and V. These are terms that tell us about the molecule and the material that we are still computing on the classical machine. But the strategy is totally different. It's a change of strategies going back to square one in a way where we have an Hamiltonian and we want to diagonalize it. So we need an ansatz for the many-body wave function. And that we borrow from what people have done from chemistry, and we need to enforce particle conservation. Okay, so now I will tell you what we do to solve our problem for this Hamiltonian. Okay, this kind of complicated slide, but I want to show you to actually give you an idea of what it takes to really get to then have numbers that make sense, and they are for a realistic system on a quantum computer. Okay, so you have your solid, you need to do a density functional theory calculation at a certain level. Then you need to do a calculation for quantum embedding, not trivial at all. You have to know how to also compute excited electronic states. Remember to have this term that I told you is important. Once you have this, you determine qubit Hamiltonian. We borrow this for all the Python script that others have done. And then we use a variational quantum eigensolver to have the ground state of the electrons. And we use a quantum subspace expansion to have the excited states. These are two algorithms that have been developed and that we use, like we use other algorithms on the classical computer. To do this, we have to couple a number of codes that either are out there or that we ourselves developed. And for example, the last one was taken from Garden Chen groups. The first one is a very well-known electronic structure code, Quantum Espresso. And then we use Qiskit to do, which is available on GitHub, to implement our version of MICCoM and QSC. Okay, so by doing that, we did the first simulation of a spin defect on a quantum computer. This is an MV minus in Diamond. The picture down there is to tell you that the calculations on a quantum simulator before going on quantum hardware are correct, because they actually are the same than on a classical computer. And these are the simulation on a quantum computer. First of all, the results depend on where you start. That already is not the greatest of thing that you want to hear. But what do I mean by that? We converge, but in some cases, there is a convergence to a result which is higher than 0, which is our quantum simulator classical results, and because of the noise of the quantum hardware. And so this was the first calculation we did for the ground state. Then we learned how to do excited states. So let me tell you really quickly the two main problems that we tried to tackle. So this is a minimization of the energy as a function of the number of measurements that we do on the quantum machine. And the blue line is FCI, full CI, meaning the calculation that we do on a quantum, on a classical computer. The very first thing that when we went from diamond, we didn't notice in diamond, but from a more complicated system, is that our variational eigensolver was not apparently variational. Numbers below, here, because of noise, we didn't notice for the ground state, but here they go below. So what's going on? So what's going on is that due to the noise and also to a very tricky, we can discuss about that difference between the Hilbert space of the Hamiltonian on quantum gates and your second quantization Hamiltonian. The number of electrons is not always conserved. And so if it's not conserved and the constraint is not satisfied, you go below. And so we found a way, forget about what, this graph is a little bit too complicated for a talk like this, but so we had to impose a constraint, and we did this through a post-processing mechanism. By the way, you see this when you try really to solve a realistic system. If you don't try to solve a realistic system, you probably, and just a very minimum model, you don't see this. So after doing this, we were in business again. You see down here, the energy did converge, and of course now there is noise, and we have to deal with noise, but converges above the limit. And then we need to extrapolate noise. So if you look at those numbers, this noise, these are electron volt, is not small. And by not small, I mean not small compared to the energies that are interested for our system, for our problem. So for the noise, we did an extrapolation with split exponentials, and there is a paper on the archive, and it will come out soon, where we actually split the measurements on the qubit in a specific way so that we reduce the noise by doing a split extrapolation that will remind you, if you look at this, of a Trotter-Suzuki formula. So now we have our system, we have done our quantum embedding, we run it, we impose a constraint on the number of electrons, the algorithm is variational, we extrapolate, and we have results that I will now tell you about in a table. So you will see tables full of numbers where I present classical results, full CI, and QC, quantum calculations, to tell you how well or how badly we can do. So these states here are just energy differences, and these kind of symbols, of course, to the experts, they will be very clear. They are states labeled by the irreducible representation of the groups of this system, but to the non-expert, they look funny, but they are just transition from one state to the other, and it's just a way that we use to label these states. So they are energy differences. So you see, if you don't do so you just correct for the number of electrons for the non-variational aspects of the algorithm, you get results that are not too bad, but not too good either. And here, when you use mitigation technique, for example, if you look at this mitigation technique, you get results that are better. 512, 511, 50, and all these results. However, there are results that are not yet better. These states are degenerate. We know they are degenerate, but if you didn't know, there would be a lifting of a degeneracy here that is not good. And we are still struggling with that. And these are electron volt, by the way, okay? And we are still struggling with that. And we talk in our paper about, the technicality of how we extrapolate noise. So good news first, in the summary of this quantum embedding, we solved the electronic structure at t = 0 of realistic point defects in solids. So this is actually quite a good accomplishment, in my opinion. We still have plenty of problems. First, we do not yet know how to evaluate hard bounds on the performance of the algorithm in the presence of noise. I told you we evaluated this, right? These bounds that we can now translate to other defects or to other problems? We don't know. If I change the number of states where I start, the starting states, for another defect, do I have the same noise? I don't know. So the reason why we want to learn about doing calculation on a quantum computer is that there is a hope, although not a bulletproof demonstration, that actually, instead of having an exponential growth as a number of particles, as what I have when I do full CI, I will be able to diagonalize Hamiltonian in a polynomial runtime. Okay, this is why I'm learning all this. So this is why I want to do this, because quantum computers do hold the promise to give me algorithms that are much better scaling than a full diagonalization of algorithm on a classical computer. However, I told you over and over again that we still have very large prefactor of to the polynomial runtime, even if we believe that the runtime is polynomial. In addition, we need to move. We still need to move data from classical computer to quantum computers, and these data better be not too big, because otherwise the quantum advantage that one day we will have may disappear, because there are bottlenecks of data transfer. And I only told you about fermionic Hamiltonians, and of course the material science problem is way beyond the fermionic Hamiltonian. If you want phonon, vibrational states, electron phonon, as I told you at the beginning, you need to be able to solve other Hamiltonian. But this is, and by the way, there was a beautiful paper, in my opinion, 3 years ago out of Fermilab, where they did try to do an electron phonon system on a quantum computer. Okay. So I have, I guess, 2 minutes or 2 or 3 minutes, and I want to just tell you what we are doing on spin qubit on classical computer. And so while we are learning on quantum computers, believing the promise that there will be better scaling algorithm and trying to learn how to attack that, on classical computers, of course, we are putting a lot of effort to study multiple property of spin defects, the one that motivated really our quantum embedding theory. And they motivated it because there are states of these qubits that you cannot solve by DFT, but you need highly, they are strongly correlated system. And so this is why we wanted to have a higher level of theory described with adaptive space. I didn't insist too much on that, but this is really what brought us there. So in the classical computer, we want to study two-level system to realize qubits. And for different quantum technologies. The first papers that started talking about this were more than 20 years ago, David DiVincenzo, and then 10 years ago, Van de Walle and Ashalom, wrote down, if you have a qubit, if you have a defect in a solid, what are all the characteristics that you have to satisfy to have a qubit, and so on. And there are other reviews recently, including one of ours that we wrote during the pandemic to say, okay, what are all the characteristics of a two-level system of a spin qubit in the solids that we have to identify promising defects. And the electronic structure that I told you about is just one part of all the integrated strategy that we are trying to put together to study these qubits. So here you see a summary of our strategy. So I told you about the quantum embedding is here for the correlated excitation that led us to try and use quantum computers. The quantum embedding comes from solving all the properties with DFT and even advanced sampling on defects. And then the other thing that we need to know how to do is to understand coherence times. What I mean is you have a spin qubit, you satisfy all the material properties that these qubits must have in terms of where you want the states in the gap of the system, spin orbit coupling, whatnot. But then you want to prepare your spin qubit in a state, you want it to stay there, and you want to create entangled states. However, your spin qubit, electronic spin qubits, interacts with the ions in the system, the nuclear spins. And so the coherence, after a while, it's lost. Can you compute coherence times? And this is a very interesting problem also from the computational standpoint. And we use spin Hamiltonians to do spin dynamics of defects. Sorry, spin dynamics of the spin qubit. And all the parameters of that Hamiltonian, which by the way contains a magnetic field, B, are computed again from DFT. And we built on the work of Yang and Liew. They were really pioneer in more than, almost 15 years ago to look at these problems. And we are able to compute coherence times, and we are also able to understand entangled electronic and nuclear spins. And we have done this recently. So I'm just mentioning it in case somebody's interested, but of course, I'm not going into any detail at the very end of my talk. So the dream here would be to, while we do simulation on quantum simulation on materials on classical computer, is to be able to be so good that we make prediction of devices that are then really devices that you can even use to build quantum technologies, including a quantum computer that can in turn give you improved prediction of materials that then you can deal with, of course, if the promise works out for the scaling of the algorithm on a quantum computer. So this is my group in one of the first day in September last year when we got back together. And now, in the last few months, it has been mixed. The people here are most of the people who did the work that I mentioned here and there. All the codes that we have developed and also optimized from other codes have been developed and are developed within MICCoM, which is a computational material science center funded by DOE that has been going on at Argonne since 2015, and a lot of development of quantum algorithm in the QNext hub at Argonne. And my work is also funded by NSF, DOD, and these are some of my senior collaborators. And with this, I'd like to very much thank you for your attention. And of course, I'd be happy to answer any question. Thank you.
Thank you very much, Giulia, for a really interesting talk. So yeah, we have a good amount of time for questions. And I think that, unfortunately, this isn't a funny webinar format, so I'm not sure if people can actually unmute themselves to ask questions, but if you can't unmute yourself, you can just enter a question in the Q&A, and I will read it and give Giulia a chance to answer. So a question from Craig Carter says that was an elegant talk. Thank you. First question is, oh, Craig, can you, you've appeared in the Zoom. Maybe you can.
Oh, Yusuf, it's fine if you just want to read it. It'll be more efficient if you do so. But thank you. And
okay.
Beautiful talk. I enjoyed that.
Thank you.
So Craig says, first question is, you mentioned that the method is impractical for defects that are not very localized. Can you say a bit more about what the practical limitations are?
Yeah.
Is it computational time, algorithm complexity, other things?
Yes. Actually, you know, this paper here, oh no, it's not. So we have a paper that we are finishing, and we hope to send to JCTC, Journal of, JCTC. To actually, this is a paper on your question. So, okay, let me try to explain. So we, yes, so we needed to, so the way the quantum embedding theory is set up here, and the way based on the Green's functions formalism, you know, I don't know how much. Let me give you a super technical answer, and then I'll try to explain better. So in our quantum embedding theory, the off-diagonal elements of the self-energy between the environment and the active space are neglected. So said in, you know, better words, maybe what we mean is that we need to be able to define an active space with that contains states that yes have the effect on the environment on them, but they don't have a very strong hybridization with the environment. So they may have some hybridization that is contained in their localized states, but the hybridization between the active space of the environment is not considered. The reason why we wanted to have this, so there is a theoretical limitation, okay? The reason why we developed all this in this way is because actually the first motivation really that we had, and the reason why we wanted to do this, was motivated by our physical system. So the physical system that we wanted to study was a system where we want the states to be localized, because this is what will allow us to do a spin qubit. So there is a theoretical limitation. Within the theoretical limitation, there is also computational limitation, in the sense that even if the states are localized, you cannot include too many states, because on a classical computer, you need to do full CI. In full CI has an exponential scaling, right? So, so this is then what led us to think, okay, how can we beat this? Of course, you know, there are other quantum chemistry methods and blah, blah, blah. But then it made us think, okay, maybe we can really beat this with a quantum computer. And then you know, we realized that the learning curve was very steep for the quantum computer. So short answer, one theoretical limitation. And then even if this is satisfied, there will be a computational limitation. I hope this gives you at least an idea to about the answer to your question.
Yeah, thanks. I'll let Craig pipe in if he has any follow-ups, but there's a second question, or it says it did. Is the split exponential extrapolation to zero noise ad hoc, or is there something more physically fundamental to that choice? And if ad hoc, or have they tried different models for the extrapolation?
Yeah, that's a very good question. So so it's not ad hoc in the sense that you can use it for as many qubits as you want, although, first of all, we don't have access to as many qubits as we want, but so in the sense that it's scalable, and we do the split exponential in a way that you can apply it. So it's not ad hoc for the circuit that we have. It's not ad hoc for the specific system that we have. And then if you ask me, will it work well for any other problems of that type? I don't know. I don't know that. I'm not sure I know that answer. But it's not ad hoc. For the circuits, it's not ad hoc for the system. And if you have a molecule, so what do we want to do now, right? If suppose one thing that because I'm obsessed. Another system I'm obsessed with is water. Studying water and stuff like that. And I want to study ions in water, and I want to consider ions as defects in water, and I want to study correlated state of these ions. Okay. I could do that if I can do many, calculation for many configurations of water. And it will not be just physically motivated by my system. I could do that if I have a molecule on the surface, for example, which is the other thing that I would like to try and do with the quantum embedding. Whether I can really do this extrapolation as well, here, whether this extrapolation here would work as well, I don't know. That I don't know. So by the way, this is, I choose to talk about this work because of course we are excited about this, it's new, but because I wanted some feedback. This is one paper we have written on that, and we need to go, we have a long way to go to gain some experience here.
Makes sense, thank you. Other questions from the audience? I have a very naive question because I have no background at all in quantum computing, but Giulia, you talked about the prefactor for some of these quantum algorithms as potentially being a challenge. And I was wondering, could you explain that in physical terms? What might contribute to the prefactor being large?
Yes.
Or any intuition, just
so if you're wondering why I use this stupid way to go between view graphs, is because yesterday my Zoom crashed so many times when I went back and forth from PowerPoint, and now I don't know why, and I'm worried. Sorry about that. Okay. So, there are several prefactors. There is the prefactor of building the effective Hamiltonian first on a quantum, on a classical computer, and doing all these calculations that have a scaling that is not innocent. There is a scaling here for the basis set that we use in DFT, that it's of the order of n to the third or fourth, but we have a scaling which is n to the fourth, n is the number of electrons for our quantum embedding. But then we also, there is a prefactor in how we prepare the wave function. And in the prefactor, I actually included how many measurements we have to wait to obtain an average. So let me tell you something that I should have said. So each of these points here, each of these orange point or that you see, each point is one, in this specific example, 1,800 measurements to average. So you see each of these points, you see this small error bars here before even talking about noise. You know, I didn't explain this, but this is the error bar of the measurements. I have to do, you know, to prepare my wave function and measure it on the quantum hardware many times and averaging. And then I get this point. Then I get this, which doesn't even conserve the number of electrons. And then I need to do all this extrapolation, and then I have to extrapolate for noise. All this builds to the prefactor in a very, very important way. So by the way, you know, IBM and also others, they provide way of doing the averaging in a you know, in an efficient way, but still you have to get this error bar of the single point down, otherwise you cannot even start. So many, many free factors.
Yeah, makes sense. Thank you. I realize we're at the top of the hour. There's one more question if you're willing to stay on for one more minute, but
Sure.
And anyone who needs to go, of course. This is a question from Vrinda Samjit. So thank you for the very nice talk, Professor Galli. I was wondering if simulations using quantum hardware are generally advantageous over those on classical hardware for systems with strongly correlated localized electrons. Or is there a rule of thumb to identify research areas where simulations using quantum hardware become advantageous over those using classical hardware?
Yeah, that's an excellent question. So yes, I think that you know, strongly correlated systems for which and this is really what led us, as I said, to the embedding, to really do strongly correlated systems. And I think this is an area, if really we can have a polynomial scaling when we diagonalize our Hamiltonian, this is definitely an area where this will be advantageous. I strongly believe that. Absolutely, you are right. Strongly correlated system. By the way, all the states of these defects, I didn't show you all the diagrams and blah, 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 because this was not the point here, but they're all strongly correlated states. They cannot be described by a single reference. I mean, by a single Slater determinant. They cannot be computed by DFT. And this is why we went to do a quantum embedding, and only later, you know, I told you the story from the end, but only later we understood that we could also run it on a quantum computer. But, you know, we really went to do the quantum embedding because we wanted to study highly correlated states.
Perfect. No, thank you.
Sure.
Okay. I think we're out of time, and we've covered the questions we have. So let's thank Professor Galli again.
Thank you. Thank you so much for having me.
No, thanks for taking the time.
Thank you.